The title of today's chapter is a new concept, limit cycles. And the whole idea is to understand by the end of the next hour and a half what the heck a limit cycle is. And because it's the new thing in two dimensions. We already had one new thing, which was centers, and limit cycles is what happens when you have an unstable spiral, right? So you had some fixed point, which usually we put at the origin, and if you start off a little bit away from that, then you spiral outward, and then the question is, what happens? And the typical answer is that you wind up with some trajectory which is periodic of a finite size. That's the typical thing that happens, and that thing is called a limit cycle. So a limit cycle is an oscillation of finite width, radius, amplitude, whatever, around that sort of, built around an unstable spiral. It's the end result of an unstable spiral. All right. So there's a trivial, the simplest possible example of a limit cycle is the following very complicated equations, which we're going to write in polar coordinates. R dot equals R times 1 minus R squared, and theta dot equals 1. All right? So now there's no fixed point of this motion except the point R equals 0. The R point out, well, right? The theta is just rotating, but if the radius is 0, rotation doesn't do anything, and so really the origin is a fixed point, right? You have, and this is an unstable fixed point. Why? Because you just have to look at the R dynamics, right? If you have, for small r dot equals R, and therefore it grows the radius grows exponentially. And then, however, we look at the R dot as a function of R, we see that it looks like this. And so there's a stable fixed point at R equals 1. Right? R equals 0 is an unstable fixed point of the R dynamics, which is a one-dimensional dynamics. And R equals 1 is a stable fixed point because it's got a negative slope there. Well, back to the first lecture. All right, so in other words, what happens is that if you start out, say, R equals a half, then theta starts increasing, and then eventually you wind up at R equals 1, and it just keeps rotating around R equals 1 at infinite time, right? The radius approaches 1 exponentially slowly as t goes to infinity. So that is the circle at R equals 1 is a limit cycle, the simplest possible case of a limit cycle. So that's kind of too simple. And now let's talk about something that's going to be the subject of most of the talk today, is the van der Pol oscillator, which is the following equation. It's an oscillator, so you have x double dot plus x equals 0, plus there's another term here. And the other term is, let's get the signs right, plus mu x squared minus 1 times x dot. All right? Now, so what's going on here? So this we understand, x double dot plus x, that's just a harmonic oscillator. And now there's a kind of friction term here, because it's proportional to x dot.
X גם לא צריך להיות עם קבוע?
סליחה?
X גם לא צריך להיות עם קבוע מסוים? צמוד אליו?
Acronite, but why? I mean, why bother? It just makes, you want me to write omegas everywhere, just for the hell of it. We define time so that omega's 1, right? We're working in units. We redefine time so omega's 1, right? Okay, so this is, as generic as anything, right? Now, the idea is that there's some kind of friction, but it's actually not just friction. It's because if this term is, if I just had written minus, right? The typical term is x double dot e plus. If I had just the plus term, if I had just plus mu x dot, that would be standard friction, right? That would be a standard damped oscillator. But now, notice that when x is small, in fact, mu has the wrong sign. It's a negative number. So when x is small, in fact, there's gain, not friction. There's anti-friction, right? You're pumping energy into the system. So for small x's, when x is less than 1, then you have gain. And when x is greater than 1 in magnitude, then you have loss. So what happens is, if you start out with some small x, the system is a harmonic oscillator, it's rotating, right? But there's gain in the system, so the energy is going to increase. And the energy is going to keep it, so the radius is going to grow. The amplitude is proportional, right? So the amplitude is going to grow and grow and grow. Eventually, x gets so big, right, that this term changes sign. So this term keeps changing sign all the time because x, when it's oscillating, right, x is going between some maximum value, some minimum value. And so this thing is changing sign, but if x is big enough and spends enough time being quenched rather than amplified, and so eventually this thing settles down to a final motion, which can look very weird. So the path, just pardon my drawing skills, but it looks, for some value of whatever the picture in the book, looks like something like that. That's what it looks like in x dot space, right? Instead of being just a nice little circle in x dot space, which would be the case here, it looks pretty weird, and it doesn't look much better in x as a function of t. Also, it's a pretty weird thing. All right. So anyway, the point is that because x equals 0 is an unstable limit cycle, an unstable spiral, because the x dot term for x equals 0 is the minus sign here, which means it's unstable. If you work out the linear stability analysis, it's an unstable spiral here, and therefore it develops into this limit cycle because at large x's, this term stabilizes things at large x's. Okay. The fact that you understand that it's if you do linear analysis around the origin, right? We write down the Jacobian matrix and do blah blah. What you'll find out is that there is a complex. There are two eigenvalues, and lambda is some plus some real number, plus and minus basically I omega. Because omega's 1, right? So it's rotating, but it's also growing. So it's an unstable. So that's an unstable spiral, which is constant. Which is the radius is increasing exponentially with time. And then the point is that there's stabilization at large x because that changes the sign of this term, and makes sure that there's damping at large x. And whoa. Okay. Now, we're going to spend most of our time talking about this in two different limits. So I actually wish we should do that first before. That's not the order that Strogatz does it, but since we're here, we might as well just talk about it. So you would like to analyze this thing. So in general, for arbitrary mu, the only thing you can do is hand it to MATLAB and have it draw pictures for you, right? But there are two limits in which you can actually analytically discuss what's going on here, right? The simple limit is large mu, when mu is very, very large, all right? And that's not trivial also, but it's easier than the other limit, which is small mu in some sense. So we'll do the large mu first. Okay. So what happens when mu is large? So if mu is large, generally speaking, since x is not always equal to 1, right, this term is very large. Now x as we'll see, doesn't get that large. X, in fact, we'll see goes between 1 and 2. So x is not getting between, between minus 2 and 2. X goes between minus 2 and 2, so that's not very large. This term, however, is very large, and therefore the only way to make things work is we need a second term to balance this term. We need two large terms to cancel, so the sum has to be 0. And this term is large, this term can't beat it. Right? This term can't cancel it, so it's this term. So basically, the approximation is to say that this term is basically irrelevant, and it turns out that the acceleration is very large, and so these two terms balance each other. That's the basic physics of what's going on, the basic understanding. And if that was the case, in fact, then we could solve the problem. If we throw out this term, in fact, we can solve the problem. So what do we get? We get that x double dot plus mu x squared minus 1 x dot what do we want to say? Yes. Okay, hold on a second. Right. Okay, so now equals 0. So what do I do with this? Well, notice that this is the time derivative of x cubed mu times x cubed over 3 minus x. Right? This term, if I take this and take a dot of this, I get x squared minus 1 times dx dt, which is x dot. So this is, and the integral of this is x dot. So what I get is that this is a constant. All right? All right, so that's basically that's the underlying behavior of this system. Is the system wants to keep this thing to be a constant. Okay? But it can't, as we'll see, it can't do that all the time. So, but it spends most of its time with this as a constant, and then things happen, but basically this is so given that this thing is, so it turns out that it's not really a constant because this is an approximation, but in fact it is, so what we're going to do is we're going to define but it's small, and we're going to write, so it's not exactly 0. We're going to say that it's mu times omega, a new variable. All right, that's the definition of omega, if you will. Omega is defined to be x dot plus that thing, and because the idea is that the system wants to arrange things so that W is basically constant, at least we'll see what happens. All right, given that, and now let's look at the derivative, time derivative of this thing. The time derivative of this thing now is just this thing, x double dot plus mu x squared minus 1 x dot, right? Because that's how we got this, right? And now, minus mu equals mu w dot, but x double dot plus this is in fact exactly equal to minus x. So we get that w dot, so this is minus x. So we find that omega dot equals minus x over mu. All right? Which means that since mu is very big, and x is of order 1, omega dot is very, very slow. So, right? So omega is what's called the slow variable, because its time derivative is very slow. Okay? So it's not exactly constant, right? When we said that we originally, our approximation, our first guess at things was it was a constant, and that's too much to expect because we dropped the term, but it does mean that in fact, as we'll see, it's a slow variable. It changes, but very, very slowly. All right? And now, so that's one equation of motion. The second equation of motion is this equation, right? X, so we have our two equations. X dot equals mu omega. So it's mu times omega plus x minus x cubed over 3. And omega dot equals minus x over mu. Now, just like because omega dot was something over mu, meant omega was a slow variable, by the same token, x dot is proportional to mu, and mu is very big. So this x is the fast variable. Okay? Yeah.
X represents the location of the...
Is it of the oscillator?
Yeah,
Right?
of the
The x is x, right?
What does omega represent?
Ah, well, that's
Like
that's the whole trick, right? I mean, we'll see. I mean, it's not obvious, right? And that's why I mean, it's the deviation. Omega is the deviation from, this what it wants to do when mu is in what it really wants to do. Can't, right? As we'll see in a minute. But it's not, it's not, there's no word for this. It's not a momentum or anything like that. It's a very complicated beast. But on the other hand, it's what enables us to simplify the system because we identified what was happening for large mu, and now we're treating what's left over sort of as like a perturbation almost.
You
Right.
said that, I mean, the name of this equation is the Van der Waals
Paul.
oscillator.
Right.
So omega is, so there's some, omega must be some...
Well, x and omega both are periodic in time, yes,
Yeah.
as we'll see.
So the solution of x will be like some sort of...
No, you
oscillator.
can't guess it yet.
Ah.
Just hold your horses.
Okay.
Yeah.
Okay. So over there, you said that x is between -2 to 2, right?
Right.
Okay. So when you say x is fast, it's like
It's changing quickly.
okay.
It's
so
going.
change
It's
quickly,
not.
but
It's
not.
not. It's not moving from -50 to 50, but it's moving from here to there.
So you
super
said
fast.
that you said that x is irrelevant because mu is big and
Well, it's
It's
okay. It's not.
double dot
Okay.
is
So
big.
now we're in a situation like we were in the situation when we talked about the super overdamped oscillator. Right? That we started out with a two-dimensional problem, and we found out that basically it was a one-dimensional problem, except there for the initial conditions. Right? The system had to equilibrate first, and then once it did that, then it was basically a one-dimensional system. It's basically almost the same story here with a couple twists.
okay.
So now that's what we're talking about. So let's wrong way. Okay. Now, so we have these equations. So now, okay. So, all right. So there are two possibilities in life. Either this thing is not zero, and in which case x dot is very big, and then if it's zero, however, x dot can then be normal, because if this thing is small, then x dot can be, even though it's got a mu in it, this thing will be, x dot will be normal. So in fact, what happens is, let's draw this curve in the omega x plane. Right? This is 0 means the w equals minus x plus x cubed over 3. So it looks like that. Right? That is the nullcline. Remember the word. This is the nullcline of x. If for all the points on this curve, x dot is 0. Right? So what happens? Okay, so now let's start the game. Say we start the game with this initial condition. Let's go. We'll start here. Say, all right. We just pick a random initial condition. Okay, and now we're above the curve, so therefore x dot is positive, right? And x dot is huge. And whereas omega dot is slow, so basically omega is not changing, and basically the path is a straight line till you hit that. And now what happens is now the particle is happy. X doesn't want to move very much doesn't want to move much at all because x dot is almost 0. It's sort of no longer huge. In fact it's x dot is small now. And what happens is that x is now slaved to omega. And follows, because here omega dot, and here omega dot is negative, because x is positive, so omega dot is negative, and you just go down, down, down. Right? Yeah.
Why is it not why does it go in a straight line there? Not
because
angle?
omega dot is, there is an angle, but it's 1 over mu,
small.
and mu
Okay.
is 1,000,000, so therefore it's essentially flat. Right? Now you kept on, so you go slowly, slowly, slowly. Omega is changing, right? We know how big omega dot is. Omega dot x is, normal size. X's we'll see, are 1, 2, whatever. So omega dot is normal. X is normal size. Omega dot is 1 over mu, and now x is now slaved. X of omega is the solution. Is given by the equation. Is determined by the equation omega equals plus x minus x cubed over 3 equals 0. So given an omega, x changes to keep up with it. So x is now slaved to omega, right? And because it's just moving along, omega is just changing slowly by this equation. And x is sort of dragged along for the ride. So x is changing very slowly as well. Everything is changing slowly here. Because omega is changing of order 1 over mu. And x, right, if you think about what x dot is, because, what do I want to say? So x is also moving very slowly here, because it's just given by x dot is proportional here to omega dot, and therefore omega dot is of order 1 over mu, so x is also moving very slowly here. And now what happens here? All right, at this point, at the bottom here, omega dot can't, it keeps, omega dot is still negative, because x is still finite, right? X is whatever it is. Omega dot, and now you can't follow once you're here, once omega drops here, there is no x anymore. That's on the null line. So what happens? You zoom to here. Right? You have to leave the null line, because you ran out of the null line. You sort of ran off the cliff, and you fall super quickly to here. And now in this region, x is negative, so therefore omega dot is positive. And you start climbing very slowly. Because omega x is again is order 1, right? And until you get to here. And then again, omega dot is still positive, so you get a little bit above the null line. The minute you're above the null line, you go zoom to here, and this is the oscillation. And so the oscillation has two different regimes. It's got the slow regime, and where you're going down here and going up here, and it's got the super fast regimes where x is changing rapidly, is changing super rapidly. So if you look at the curve, what does it look like? X of t looks something like it's changing slowly and then whoop, and then it's changing slowly and whoop, and changing slowly and whoop. It looks like that kind of almost sawtooth, but not exactly sawtooth, because these are smooth curves here. These are jumps and basically jumps, and these are smooth curves as you're going up and down over here. So that is the motion. All right. All right, so that's different than in the case of the overdamped pendulum. You never had to leave the null line, so you just kept going to the fixed point, and you died, and you just went to sleep at the fixed point. Here, you keep going around, and the only way, because it's a one-dimensional motion here, right? And we know that you can't have oscillations in a one-dimensional motion, right? Because we learned that. So the way you get an oscillation is you have to go off into the second dimension, leave the null line, jump to the other side, and so it's it's piecewise. Not until you build the oscillation out of these little different segments. Okay, and so you can calculate, for example, what is the period of the motion. How long does it take to do this? Well, how long does it take to go from here to here? A time of order 1 over mu. So that's it. That's nothing. How long does it take to do this? Also a time of order 1 over mu. That's nothing. All right? And now, all the time is spent on the slow parts. Right? So now we have to figure out where they are. And if you think about it, the bottom here, where is the bottom of this curve? This curve, remember, is W omega equals x minus x plus x cubed over 3. Right? So the bottom here is where? Is at the minimum of that, which is, so therefore minus 1 plus x squared equals 0. So x equals 1. So this is x equals 1. Right? That's that value of x. Now, what's this? And now, at that value, what is the omega? Omega is minus 1 plus a third, right? And therefore, it's minus 2/3. Right? So now we have to figure out where this point is, because this is back on the null line with a value of omega equals minus 2/3. So we have the equation that minus 2/3 equals minus x plus x cubed over 3, and the answer, I believe, is x equals 2. Because is that right? Did I do that right? Let's see, because we get minus 2 plus 8/3 is 2/3. And what did I do wrong? X is minus 2, right? X is minus 2, and therefore this is 2, and this is minus 8/3, and that's equal to. So the solution is x equals minus 2. So this is the point x equals minus 2, and this is the point x equals minus 1 again, and this is the point x equals 2. All right. So those are the slow thing is from x goes from 2 to 1, and then that takes a long time. And then it has to go from minus 2 to minus 1, Now the time it takes to go from -2 to -1 is the same time it takes to go from 2 to 1 because everything is symmetric. So the period is twice the time from x equals 2 to x equals 1. Right? Now, the time, what we have is the time is, so the time, it's, the period is twice the integral from d omega over omega dot during this period of motion, right? From whatever value of this is, I guess this is, by symmetry, this is omega equals 2/3, I guess. But we're going to change variables because d omega along the null time, d omega is the derivative of this. It's -1 plus x squared dx, right? Because we have this equation, that's the null line, and omega dot equals minus x over mu. So you can change now variables to integrate the x times 1 plus x squared, 1 minus x squared, excuse me, or x squared minus 1, appropriately, over, and then we have over x and times mu, and it's the integral from 1 to 2.
Also need a minus sign there.
I think I got all the minus signs correct. This is x squared minus 1. I changed this from 2 to 1, right? And so everything is kosher. This is a positive number. And you work it out. You can do the integrals, in your spare time. And the final answer is somewhere, is mu times 3 minus 2 log 2. So the point is that it's very big because going along these null lines, it's very slow. And therefore the period is very long. Yeah.
I was going to ask why is the t from x equals 2 to x equals 1 is the integral, but I think I understood.
You can write it in omega as minus 2/3 to 2/3, right? If you want to think of it that way, actually it's, but the point is I change variables to x, that's all. It's just more convenient. All right. So that is the one limit of the Van der Waals oscillator, and you see that it goes from 2 to 1, and then it goes from -1 to -2 to -1, and then it goes from 2 to 1, and then from -2 to -1, etc., etc., and with jumps in between. All right. So that's the large mu limit of this game. Okay, so now that's what happens at large mu. And now the question is what happens at small mu. And what happens in between is go ask MATLAB, because that's the only one, it's the only person who's going to be able to tell you that. Before we deal, okay, so now we have an oscillator, and now with a weak perturbation, because mu is very small. Right? So the obvious thing to do is to do perturbation theory, right? Because I have the zeroth order solution, right? X double dot plus x equals minus mu x squared minus 1 x dot. Right? I say that x naught equals a cosine t, say. Right? And now, plus order mu. times plus mu x. So x equals x naught plus mu x1, right? Because this satisfies to leading order, this satisfies that part, and this is a perturbation which drives, I can think of this as a driven oscillator, right? This is an oscillator, now you have an equation x1 double dot plus x1 equals minus x naught squared minus 1 times x naught dot, right? And so where x naught is given by a cosine t. So it's a driven oscillator, right? Because that's an oscillator when you have a function of t on the right-hand side, that's a driving term. Now there's only one problem. Now we can solve that. I won't do it because it's a pain, right? But it's a problem. What's the problem? Because when you do that, you see that there's, for example, the x naught dot term, which means that you're driving it periodically at the same frequency as the oscillator. And this is not a damped oscillator, this is an undamped oscillator. So you're driving it in resonance. What happens when you drive an oscillator in resonance? The amplitude grows. They're called secular terms, right? You get what's called secular terms. You get terms which grow like t. So in next order perturbation theory, you get things like t sine t or t cosine t. And the amplitude of the oscillator starts growing. And now it's not oscillating anymore. It's just growing. And we know that this thing is supposed to oscillate, and it's no longer oscillating. So this perturbation theory does not work. We got to do something else. So before I'll tell you what the other thing is, let's talk about a simple problem where we can solve the problem exactly and see what's happening. Let's talk about the following trivial problem. X double prime plus x equals, instead of something carbon and messy and complicated, we're going to do something nice and linear, equals 2 mu x dot. Minus, right? I want minus, I want, right? Yeah. Right, that's what I want. Signs always a problem. Yeah. Right. Okay. So here, this is a simple, pure damped oscillator. Right? And what is the solution? It's an exponential, complex exponential, right? X equals a e to the alpha t, right? Where alpha satisfies alpha squared plus alpha equals 2 mu plus 1 equals 2 mu alpha, right? So therefore, and of course I got it. No, okay, I got it wrong. This is x. Hold on a second. I think I got the sign wrong. I always get the signs wrong. 2 seconds. Where is it? Plus. So it's minus here. Yes, minus here and minus there. That's right. Okay. So now alpha. So I have alpha squared plus 2 mu alpha plus 1 equals 0, and therefore alpha equals minus 2 alpha mu, right? Plus or minus the square root of 4 mu squared plus 4 over 2, which is minus mu plus minus the square root of mu squared minus 1, and therefore this is, okay, since mu is small, the square root of minus 1 is plus minus I minus mu, right? Plus something times mu squared plus whatever, right? But mu is small. So therefore, what does this thing look like? We know what it looks like. X of t is a e to the minus mu t cosine t. Say. Right? It's a damped oscillation. Right? And this is the leading order solution. And now if I expand, but mu is small, you said to me. Right? So why did I write e to the mu t minus mu t? I can expand that. And if I expand that, then I get a cosine t, right, which is our 0th order solution, right, times 1 minus mu t plus mu squared t squared over 2, etc., etc. You see, you got a term which is t cosine t. Right? So, but that's all, that says the amplitude is changing linearly in time. But that's a lie. In fact, it's slowly decaying in time. Right? And the perturbation theory, if you just do blind perturbation theory, right, you get this, you get a t term and then you get a t squared term, and only when you sum them all up do you get an exponential, which shows you that really, in fact, nothing bad is happening. This thing is nicely dying exponentially, like we know it should. Right? The problem is that how long does it take to die exponentially? Since it's a very weak damping, it takes time of order 1 over mu to die. Right? So yes, if t is order 1, then this is correct. But when this is interesting, right, is when in fact t is so large that mu t is of order 1, and you can't, the first order Taylor expansion is not any useful anymore. It's not useful anymore. So it's correct, right? But in order to get the physics out of it, to see the slow decay of this thing, right, what you have to do is in fact do perturbation theory and sum up all orders in perturbation theory in order to get what you want. That's a little too much work. It can be done. Right? But there's got to be a better way, as I say. So we're going to do the better way, right? Because we know physics. And, all right, because we know that in the absence of this term, there's conservation of
Energy?
energy. Right. Energy. We're physicists. For mathematicians, we say amplitude, but, right? I mean, conservation of energy, right? Because let's think physics, like physicists, right? So how do we do that, right? We would have multiplied this by x dot and said that this is, right? So we would define energy is x dot squared over 2 plus x squared over 2, and dE dt, right, is would have been, right, x dot, x double dot plus x dot, but x dot plus x is 0, and we would have gotten 0 for our regular harmonic oscillator. But now this is no longer 0, because we have something on the side. X double dot plus x equals, so this is now x dot times minus 2 mu x dot, which is minus 2 mu x dot squared. And what we see is that the energy is decreasing at a rate proportional to mu. Right? Because that's physics. Right? We put in damping and we get a decaying oscillation. Right? The energy is being sucked out. Right? Yeah. Okay. And now, so what we know, so let's write as solution now. We say that, and okay. So now what we know is that the solution x of t is some a of t, some amplitude which is slowly changing in time, times cosine t, right? And now, all right, so what is this thing? This thing is 2 minus 2 mu x dot squared is a squared of t times cosine squared of t. So now let's think about one period of the oscillation, right? This thing averages over to, right? Let's take an average over one period of the oscillation, and this thing averages to a half, and therefore, since A basically doesn't change at all in one oscillation, because it takes order 1 over mu oscillations before you notice that there's been a loss of energy, right? This is, we can approximate this by 2 mu. We can treat a of t as a constant, and this is a squared of t times a half, and we get minus mu a squared of t. Now, the energy is a squared of t is 1/2 a squared of t, right? Because the energy is 1/2 cosine squared plus sine squared times a squared, right? So this is a squared of t, a squared over 2. So therefore, dE dt is a dot, right? Drop one of the a's, and you get that a dot equals minus mu a, or a of t is a naught e to the minus mu t, which is exactly what we found from the exact solution, right? So this is a way to get the answer without having to either solve the problem exactly, which we don't know how to do, or summing it to all orders, which we might know how to do, but it would take a long time. In this very simple way, we have derived an equation for the amplitude as a function of time, because we know that the amplitude is slowly varying. It's a slow variable, right? Here, the phase is basically a fast variable, unless, or because it's going around the order 1, and the amplitude is a slow variable. So again, we've broken the problem into something that's moving much slower than something else. Here it's the amplitude which is slowly changing, right? And okay. So now all we have to do is do the exact same thing for our Van der Pol oscillator. Right, and yes, right. Exactly right. Okay, so now we have our Van der Pol oscillator. And we're going to do exactly the same thing. We have x double dot plus x equals, now it's minus mu x squared minus 1 x dot. Right? That's what we have. And okay. And now, again, we're going to define the energy is x dot squared over 2 plus x squared over 2. Right? We're writing x as a of t, which is some slowly changing amplitude in principle, right? Times cosine t times an oscillation, because if it wasn't for this term, it would just be an oscillator. So therefore, we have our cosine t, and now we know that that a of t is causing that this driving is causing a slow change in the amplitude. All right? And now what we have to calculate is E dot again, dE dt, which is x dot times this thing, right? As we saw before, which is x dot times this thing. It's minus mu x squared minus 1 times x dot squared. All right? Now this is a little more complicated, but not that much, because we know what x is. It's that. And we can treat a as a constant. So we get minus mu times a squared cosine squared t minus 1 times a squared sine squared sine squared t. And now we have to take an average over 1 revolution. Right? Okay. And so we now need to do 2 calculations. We have to know what the average of cosine squared sine squared is. What's the average of that? Well, cosine t sine t is 1/2 cosine sine 2t. So this is 1/2 sine 2t squared average, which is, and now sine 2t average, sine squared 2t is like sine squared t average is 1/2, just because it just does twice as much of the same thing, right? So you get, from here you get 1/2, from here you get 1/4, this is 1/8. And now, so what we have here, and then the other term is just the average of sine squared t, times a half. And so what this gives us is minus mu times a squared times a to the fourth, excuse me, right? Because you have a squared cosine a squared, and then we have this is a to the fourth over 8 minus a squared over 2. Okay, and this is 1/2 this is a dot. Right, that's a dot. Just like before. Right, so now we get the equation for A, which is a lot less trivial than we had before. It's a nonlinear equation. A dot equals plus mu over 2a minus mu over 8a cubed. So you see that A is changing very slowly. It's proportional to mu. A dot is proportional to mu, right? And this equation has fixed points, right? Where are the fixed points? There's one at 0, which is unstable, right? And it has a fixed point where a squared equals 4 or a equals 2. And that's a stable fixed point. So now we know that the motion is A goes to the stable, right? This right? A dot is a function of A, goes up linearly and then goes like this. We don't have to worry for negative because a negative doesn't mean it's the same thing as a positive because it's just 180 degrees out of phase. So you get a stable fixed point at a equals 2 at long times, right? Because at a equals 2, the loss of energy by this term exactly balances the gain of energy from this term, and on average, you're not changing the energy during a single rotation, so therefore, that's an oscillation.
You have a regular oscillation.
What?
You have a regular oscillation.
Right. Yes. So before that, if you started out with some other A, well, then A would slowly change. We could solve this equation if we felt like it, but like, who wants to do that? That's work. We don't do work, right? But we know that A slowly increases, blah, 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 over the time scale of 1 over mu until it reaches the fixed point at 2. So we solved the problem. All right? So that's the Van der Pol oscillator. And this is a general trick. This trick is called the method. It's got a name, method. You know, it's a general trick. This is the method of averaging. The idea being that you average, you have a problem with a very slowly changing amplitude. You average what's the changes over one period. So the fast variables all average out. The things that are just oscillating all average out to 1/2, 1/4, whatever. And you get an equation for the slow variables, which in this case is A, the amplitude. All right? And this works in general for all kinds of different nonlinear oscillating problems. And so this is an important thing to know. This is a very non-trivial piece of work. Yeah. Question? Was there? Okay. So that's what there is to say about the Van der Pol. We've done everything you can do except for numerical simulations to verify that this all works, but in principle. Okay. So now just a few more sort of general considerations about limit cycles, just general things. Because the general question you're interested in is, will there be a limit cycle? When is there a limit cycle? How could you tell? Right? So there are times when you know there can't be a limit cycle. So it's important to mention them, since if there's no limit cycle, then we don't want to waste our time looking for it. So, for example, yes, here it is. one class of systems that don't have limit cycles are potential systems.
Have we talked about what can we gain from limit cycles, or what?
What do you mean? What do we gain? This is a phenomenon in two-dimensional and higher dimensional systems.
Like if it's if it simplifies the system, or if it
No, it's what this. It's the long. It's a possible long time behavior in 1D, right? In 1D, what did we have? We had. You went to a fixed point, and that was the only. That was the only thing that could happen at long, or you ran off to infinity, right? But that was the only thing that could happen at long times. Is you find the nearest fixed point and you home in on it, right? In 2 dimensions, all right, we saw that there were, unstable spirals are you home into a fixed point. You just do it, by rotating into the fixed point as opposed to just clumping onto the fixed point. But it's the same thing. You're going to a fixed point, right? What's the one new thing in life? Well, we saw there was a center, which was when it was marginal, and we didn't know what was going to happen. So sometimes the center turns into a stable spiral. Sometimes the center changes into an unstable spiral. If there's conservation of energy, then you get a continuum of orbits of all radii, like we saw with the Latko-Volterra system, right? Okay, but so that's if there's a conservation law, then you get a whole family of things. But that's not generic. Most equations don't have conservation laws. Only you're brainwashed into thinking in first and second year physics that all that equation, conservation of energy is the holy thing, and that all equations have conservation laws. Well, that's true when there's no friction, when you ignore friction and you ignore all these other things. So in real life, there's and all kinds of other systems of equations like this. There's generically speaking no conservation law. So what new phenomenon is there in 2 dimensions that there isn't in 1? What can the system do at long times? Besides going to a fixed point, it can go into a limit cycle, which is a sustained oscillation that goes on forever. It's a nonlinear oscillation. You need nonlinearity to have a limit cycle. So it's a 2-dimensional nonlinear phenomenon, and it's something that we haven't seen before. So it's a possible behavior. If you're given a set of equations and you just go run to MATLAB and solve it, and you see it's going, into a circle, or not a circle, but some kind of, periodic orbit, then you say, now you have a word to describe that, you call it a limit cycle. And then everybody nods sagely and says, he knows what he's talking about.
אבל זה כן במידה מסוימת מפשט את המערכת, כלומר, זה מצביע על משהו שאנחנו יכולים להגיד עליה.
Right. It's a way of characterizing the long time behavior. It's a possible, right, exactly.
אבל בקשר לשימור אנרגיה, אבל למשל במכניקה אנליטית כל מה שאנחנו עושים זה להתעסק עם לגרנז'אנים וזה...
נכון מאוד. Right, that's a prejudice of your physics education. But if you broaden your horizon slightly, right, and you don't worry about, there are many other kinds of systems in the world other than conservative systems. Yeah. And everything and conservative systems are trivial. From the point of view of mathematicians, conservative systems are boring, right? Because energy is conserved, it doesn't do anything, it just sits there and has an orbit, has some equilibrium oscillations around around the bottom of the potential. You solve the problem. Okay, next. In here, we're looking at a much broader class of systems that do other more interesting things, like limit cycles, which doesn't exist when there's a conservation law. Right? Okay. So, but if there's a potential, then you don't get a limit cycle. What's a potential system? It's very simple. When you have the equations that x dot equals partial v, you have a function v of x, and you have x dot is grad v. That's and so you have some potential field v, and if x dot is given by minus grad v, which is the over-damped case of a real potential. If you had a real system, right, a real physical system, in the over-damped limit, this is what you get, right? Because then when we saw that we dropped the mx double dot term and we have this, and then what do we know? Is you're going to go then x then v of x v dot, right, is grad v dot x dot, which is minus grad v squared, and this is negative, so v dot is constantly decreasing along the trajectory, so you go to the bottom local minimum of v, and so I can't have a limit cycle. You're just going to the equilibrium point, which is the bottom of the potential.
מה אמרת על זה שה-x דוטיים מצטמצם?
Where in real physics, in the physics you were taught, right? Newton's physics, right?
Okay.
Right? There's another term here, which is x dotayim, right? This is the force, right? And this is the damping, right? And then in principle there's an x dotayim term. But then we said that in an overdamped system, when the damping gamma is very big, then we could throw this term away. Okay, so that's a potential system. So, for example, just stupid example, just all right. It shows you that sometimes you get it. Okay, if we had x dot equals sine y. And y dot equals x cosine y. You don't ask where this comes from, except to demonstrate that you can get a potential flow in this system, because the potential, is minus x sine y, right? And then you see that x dot is dou v dou x, right? Because you minus sine x dot is x dot is minus dv dx, and y dot is minus dv dy, because dv dy is minus sine, so you get minus x sine, and this. Do I have the signs? Oh, v is minus. Yeah, because you have too many minus signs. Sorry, you got this minus sign, so minus v cosine. Right, so this is minus x cosine is y dot, so that's correct. Okay, fine. Y plus. Okay. Whatever. Okay, so therefore, this is a potential system, even though if I just gave you these equations, it wouldn't be obvious that that's a potential system, but it is, and therefore, you don't have to worry about fixed points. You don't have to worry about, excuse me.
An exact differential will work, right?
What?
An exact differential will
Yeah,
work.
right, when you have an exact differential, right, that's how you would.
That's the idea.
Right, that's the idea. And the way you check that is you look at dou x dot dou y has to equal dou y dot dou x or whatever, because mixed partials have to be equal or whatever stuff. Okay. There's. All right. Okay. Let's see. Yeah, another system which we already know. I mean, we had the following equation: x double dot plus x dot cubed plus x equals 0, right? This is a non-linearly damped harmonic oscillator, and therefore, again, you can look at dEdt, and you find that dEdt is minus x2 is minus x to the fourth, is minus x dot to the fourth, and and that's negative, so this loses energy, and therefore has to go to 0. What else is there? Another stupid example, x dot equals minus x plus 4y, y dot equals minus x minus y cubed. Now again, you look at this, you don't know what to do with it, but it turns out by miracle that there's a, if you write down a potential function like that, then v dot over 2 is x times minus x plus 4y, and then you have plus xy plus alpha y times 4 minus x minus y cubed. And what do we have here? That you have, if alpha equals 4, then by a miracle, this term cancels this term, and we're left with minus x squared minus alpha y to the 4th, and this is negative. And again, this doesn't have a limit cycle. So there are cases which not everything has a limit cycle, but these have stable fixed points. So that's why they don't have limit cycles, right? Because there's some place to go, right? And so when you get a limit cycle is when you have an unstable spiral, right? An unstable fixed point, so you got to get out, and then where you're going to go. Well, if you're not going to go to infinity, you're either going to go to some other fixed point way out there, and right, or you're going to go to a limit cycle. That's the whole idea. And in the book, there are a couple of mathematical theorems which are just say those things in very fancy words, and they don't give proofs because the proofs are really hard, and that's real mathematics, and he doesn't deal with real mathematics. So we're left with our physicist's intuition of what the possibilities are, and the answer is if you have an unstable spiral, you look for a fixed point, right? And we actually have managed to cover. I thought this was going to take much longer, because this, I mean, the this business, the averaging and the other, and the large mu limit, those are non-obvious kinds of things to do. I mean, everything else we've done up to now is more or less, just follow your nose. And, these were, required insight and tricks and skill and stuff. That's the first times we really had to do hard stuff in this course. So next week is bifurcations in 2 dimensions. And we get all the bifurcations we saw, plus one new one, as I said, the hop. The hop bifurcation. Hop. However, it's Austrian, though. Don't ask me. I don't do Austrian. All right. So until next week.
Tutorial number 5. Last week we started to talk about a system with 2-dimensional. Okay, we talked about linear systems. Today we are going to talk about nonlinear systems. Okay, so we'll start with we have system x dot equals sum f and y dot equals sum g of x and y, and we found a fixed point, right? So that means that f at the fixed point and g at the fixed point equals 0. Okay? Okay, so what can we do? We can define u as x minus x star and v as y minus y star. So then we get u dot equal actually x dot, right? And this will be f of x star plus u and y star plus v, right? Let's do Taylor and we get f x y plus u the f the x at the fixed point plus v the I'm sorry the y at the fixed point plus some ordinary. Okay? What we want to say, we want to say that this is a small argument, right? So we want to cancel it. But this we can do only when we are not in the boundary conditions. Okay, do you remember the graph from last lecture? Okay, so in the boundaries, all the centers and what else, stars and non-isolated fixed point, we cannot do that. Okay, just in the areas between. Okay, and in the same way we can define v dot as u the g the x plus v the g the y, and we get the matrix, right? We had the matrix of the parameters, okay, that we define. So now this will be the f the x, the f the y, the g the x, and the g the y, of course at the fixed point. Okay, this is the a of u and v, and actually this is the Jacobian.
מיכאל,
Yes.
למה בשורה שם, כאילו למה כתבת את fx סטאר y סטאר? זה 0 גם ככה.
No, the
לא, למעלה.
deviation.
שורה שנייה. כתבתי אותה, זה.
here? Yes, it's 0.
Ah.
This is can't fit. Here I didn't put. It is just the tail of.
So,
You can change the marker.
Yes. This is better. Okay. Right now, reversible systems. If we can flip the time and we don't see any change, okay, in the system. So how is it defined? If we have f and g, so if we can take f of x and minus y, it will be minus f, and g will be the same. Okay, g will stay g. Of course, x and y are just symbols. You can change them by any variable. And okay, exercise. Next one. For the system x dot equal sine y and y dot equal x minus x third. Here, find the fixed points. Classify and sketch. Okay. So let's start. Let's start with finding the fixed point. So we want sine y to be 0, right? So y star will be k pi, or k is to z, and x minus x third will be 0. That means x y minus squared. So we have x 0 and x plus minus 1, right? Okay. Because this we can see that we have a period, so let's look just on a 0 and pi. Okay, we will going to look at this region. So we have the point 0 0 plus minus 1 and 0 0 pi and plus minus 1 with pi. do linearization. So the Jacobian will be dou f by the x is 0, dou f by the y is cosine y by x is 1 minus third x squared and 0. Agree? Great. Okay, so let's look at the points. 4, 0, 0. What we have? We have 0, 1, minus 2. I'm sorry, not 0. 1 and 0. Okay, that means tau equals 0 and delta is minus 1. So it will be in this area, right?
Right.
It is a saddle node. Okay. 0 pi. No, let's go plus minus 1 and 0. We have the Jacobian is 0, 1, minus 2, 0. Tau, the trace is still 0, and delta is 2. Okay? Now we are on this one. Okay? It looks like it will be a center, but in this line we cannot do a linearization. Okay? It is not, it cannot be. But, third thing, we are in a reversible system. Okay? So in that case we can do that, and so on. We have where am I? Yes, okay, so we have similar way, 0 pi, the Jacobian is 0 minus 1, 1, 0, tau is 0, delta is 1, again reversible, center. Okay, and for plus minus 1 and pi, the Jacobian will be 0, minus 1, minus 2, 0, tau is 0, delta is minus 2, and again, a saddle node. Okay, questions? Okay, great.
Why is it center if it's reversible?
Because we don't have the ordinary, where is it? This one?
In our example, why you say it's center?
Wait.
Maybe he mean you say
Wait.
twice center.
No, it is still center. It just won't be a linear center. Okay, like the jumping will be. We will see that in the sketch. Okay. Ta-da-dam. Okay, so let's see. We have here. In 0, 0, we have a saddle node, right? In 0 and plus minus 1. And we have in pi plus minus 1 saddle node, and also in this one. Okay, so saddle node, how it will be, it will go like, sorry, this, right? Around the center, this is like, this is not a linear, okay, it is not a circle, it has some shape. Okay, so it's called center, but it's just because it's like on a closed line, but it's a non-linear. Okay, so here we have like this. Here it will be the same. And we are going to continue with those points. Those are saddle, right? So it's like this. And this. this one is again okay, and this is continue also like this. No, I'm sorry, it can be the same. Let's not go here. Just a second. Yes. Yes, okay. Like this, and here we have also continue. Okay. Questions? Sure. Okay, consider the system x dot equal minus y minus x third and y dot equal x. Show that the origin is 0, although the linearization predicts a center. Okay, show that the origin is a spiral, although the linearization predicts a center. Okay, so let's start with the linearization. Okay, we have the Jacobian is minus third x squared minus 1, 1, and 0. At the origin, what we get at 0, 0, we get 0, minus 1, 1, and 0. Okay, that means tau is 0 and delta is plus 1. Okay, I erase that, but we are on the center line, right? Okay, but if we are doing a change of coordinates, we define x as r cosine theta and y r sine theta. In this term, we have x squared plus y squared equal r squared, right? That means that r dot is x dot plus y dot, right? Okay, great. And this is x dot is minus yx minus x4 plus yx. Okay, and this is minus x4. This is minus r4 cosine 4 theta. Okay, that means r dot is minus r third cosine first theta. Right? And here we can see that this is a continuous function. We don't have jumps like in centers. Okay, so it looks like we have the vector, like the eigenvector, right? In the tau going to infinity, the time going to infinity, and inside, it's not like this. and raise another. Okay, questions? Okay. You're very quiet today, we are in the last question.
זה לא כזה קריטי, אבל איך את יודעת שזה עושה ספירלה ככה ולא בכיוון ההפוך? למשל.
Because we are going to the center.
לא, אבל זה יכול לעשות גם מכיוון השני ספירלה.
Like this.
כן.
There is no reason to do that.
לא, אבל למה שתהיה העדפה לאחד ולא לשני? איך ידעת שזה ככה ולא ככה?
This is actually from the computer, like the exactly sketch.
ואנחנו זה לא כזה קריטי, נכון?
Yes, the question is it pretty? Like if the infinity, we know that it is parallel to the
כן, עכשיו אם הוא מקביל ואז עושה ככה, או מקביל ואז עושה ככה.
I don't know if we can know that just by us. Like the only reason that I think is why. Like there is no reason that it will do this.
No.
So I just continue. But like maybe. Yeah, I don't know if there is any.
אפשר לחזור רגע ללוח עצר, זה בעיה. כאילו, ויכולנו לעשות ככה, וצריך לעשות ככה.
No, that's the origin here.
כאילו,
This is the origin.
לא, עבור אותו זה. למה שזה לא יעשה
Wait.
ככה?
I think there are.
כאילו יכול, בסוף אני מניח שהוא כן עושה ככה, אבל כאילו איך אפשר לדעת? אם זה מעניין בכלל.
Actually from here, they are doing this.
לא, אבל זה עדיין לכולם כאילו עם כיוון השעון. נגד כיוון השעון? כולם נגד כיוון השעון.
Yes.
אז כאילו איך אני יודע אם האחת שלי עם כאילו נגד כיוון השעון או עם כיוון השעון? שזה סתם לא מעניין אותי, אז אני בוחר אחד.
Usually the positive direction is underwise? Underclockwise.
Clockwise or anti-clockwise? Clockwise or anti-clockwise?
No, anti. Like,
Maybe.
like yes. This is usually the positive direction. I don't know another more deeper meaning answer. Okay. Now, oscillator with both positive and negative damping. Okay, we have the oscillator x d dot plus x dot plus x equals 0. And we want to prove that this system is reversible. Okay? Any suggestion? Suggestion?
X dot equal y
Equal what?
equal y, x dot
Yes.
equal y, and
Great. X dot equal y, so y dot is x d dot is minus x minus
minus xy.
yes.
Okay.
And wait. Okay. Where am I? I'm here. Okay, so we have x, f of x, and minus y. It will be minus y. And why we have a problem here? Wait. Did I get the there is no something in the question. So why did not work? Let's try something else.
But first
No,
of all,
right? It's like plus xy. No, wait. G
still doesn't work.
will be yes minus x minus plus xy, and why did not work? Ta-da-da-da-da-da-dum.
And we'll do minus x minus y.
The first one works,
Mm.
of course.
Yes.
Sure. Because you have to put the minus again in the outside the function, right?
Here? No, but then what with x?
ממש זה יהיה הפיך, כאילו, חוץ מזה שבתרגיל, כאילו, זה ממש זוגי, כאילו, יש שם דברים, כאילו, כפל זוגי ויש כפל אי זוגי.
Good question. Okay. Wait. This. Okay. This is true. Okay, so y dot da 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 dum minus x, yes, minus y squared. And now that okay, we have minus in the squared, so we have the same one. Great. Okay. Questions?
תוכל לחזור אז מה הכוונה ברוורס אלף?
Yes. That. For example, if you look at the pendulum, and you will flip the time, you don't know about it. You will just look the same.
איך את מגדירה להפוך את הזמן משוואה כזאת?
What do I have the definition? If I take this, I want one of the variable that if I
הופך את
flip
הסימן
it
של הנגזרת וזה?
again.
הופך את הסימן של הנגזרת?
Yes.
כאילו מחליפה?
Now it's part of like we have the x like the minus t.
כן, זה מין. זה הופך את הסימן של הנגזרת, בנגזרת שנייה זה לא משנה, כי זה פעמיים.
Yes. Yes. Okay. More questions?
למה זה אומר שכאילו, why do we put f של minus y and not f של y of minus t? We're like assuming that y is a odd function.
Yes, we have a
כאילו,
f is even, and no, f is odd and g is even.
Does y also have to be even since like you're saying y of t
It
is
depends on
minus y?
it depends on f and g.
Okay. Okay.
Any other questions?
אפשר, כאילו, לא יכול, ישר מעמדה, לראות שהם מציבים מינוס t בעובד.
It's fine, but this is simple. If you want, we can just choose some another questions. Yeah, we have time. You want to do another from the book? Another question? Okay, let's try. More complex. Okay. We have the system
For which book the question?
Strobels. Theta dot equal to cotangent phi cosine theta, and phi dot is cos squared phi plus a sine squared phi sinus theta. Let's look at this now. If you flip t, if you can know, yes, actually from here is also pretty easy, right? Let's find another here.
למה בעצם פה זה טריוויאלי?
Hmm?
למה בעצם פה כאילו להפוך את הזמן?
Because it's odd and even. But okay, if it's not, let's do that. Okay, we want to see that if we're doing this flip, it works for us, right? So what we want to do, let's look at theta dot for phi and minus theta. Cot, it will stay the same, and cosine of minus will be the same, right? So it's fine. Now let's look at phi dot minus theta. Cosine squared stay the same plus a sine squared. So we have minus minus with the square. No, I'm sorry,
Well, it
it
was
is
normal.
phi still, and sinus is minus, right? So this is minus phi dot of phi and theta.
כאילו, אבל למה זה בכלל מייצג היפוך בזמן? למה
is
עם
this?
משוואה של תטא להפוך את הזמן ואת תטא לא עושה כלום, אבל לפי זה המינוס, למה זה אומר שהיא הפיכה?
Wait, I want to look what this system is for. Rotational dynamics and a phase bar trait on a sphere. The rotational dynamics of an object in a shear flow are this. So this is what it is. Like you have some argument and you just count. Yeah, I think like just in the life you're getting some equations of systems.
אבל לא הבנתי למה כאילו היפוך של הזמן ושל תטא מייצג היפוך בזמן, כאילו...
Let's think about the pendulum, right? You have r and theta on this. So you change the time, what you will see, this. So r stay the same, but theta is going the reversible way.
ולמה זה אומר שכאילו דווקא הנגזרת של פי צריכה להתהפך בזמן? למה זה פי שאני אעשה מינוס?
No, it doesn't depend. Wait, I don't think it depends on... Wait, flip here. Theta, right? Let's think on the pendulum. If theta doing the minus, the rotation, the velocity stay the same, right? Wait. No, in a pendulum like this we have. Okay, if we're doing like this thing. start here and going to this. If we'll do the opposite, we're doing that, right? So in this, when we have like in
minus
one
theta.
dimension but two, is we have minus r, right?
minus theta. minus
No, wait. No, it should be minus theta. Wait. Here theta equals some theta 0, right? And the velocity has some. Wait. R stay the same. If we are in minus theta. No, we have the same velocity. No, but R is
הוא לא כזה קריטי, אפשר להמשיך.
no, we finish.
אוקיי.
I think because we need that in totality looks the same. Like if theta is, we flip theta. Wait. Maybe it's not have to be like this. Maybe it's not have to. Like here we have r is constant, right? We cannot do minus r. And r dot, I mean r is constant. So r is always equal 0. So in this time we'll have this actually.
אוקיי.
So I don't think that it is necessary to make the flip. But interesting.
What was the question?
Why, like if we define x dot as f of x and y dot g, so if we flip y, is it necessary that y dot will stay plus y dot and not minus? Like in all the cases that we saw that it was flipped in the second one. Like we changed theta, so theta dot equal as it was before, and phi changed, and also before. But yet, like in this case, I don't think it is necessary. important thing that one is odd and one is even. This is the important thing.
כאילו אם זה ממש כאילו אחד מגדרות הנגזרת של השנייה זה כשהופכים את הזמן אז כאילו זה משנה את הסימן של הנגזרת כאילו משהו בסגנון.
Yes.
כאילו אם זה ביטוי כללי זה קצת כאילו יכול
Here if we flip the time, we flip theta, right? We did this, so we did this. But theta got also flipped. So yeah, I think it's not necessary. Any other questions? Okay, great. Good night.